All right, welcome to day 2. By this point, hopefully, in addition to turning in your regular homework, you turned in your one graded problem as well. You can pause the video here for a second and check each of your homework answers. And then because it has been a little bit since we've done these, I'm going to talk through each of the homework ones. If you got those ones correct, feel free to jump a little bit ahead to skip where I'm talking over those specific homework ones. But again, pause the video here if you want to check your answers. And then I'm going to skip ahead and talk a little bit about each of the homework ones. So in one, multiply your dx over, divide your square root of y over. Do your antiderivative of both sides. Sub in our point to get the c is negative 12. Rewrite your equation with the c filled in. And then we'll divide by 2, take the square root, and that gives us our equation there. No issues in the equation with things that could be undefined. No issues in the original differential equation. Um, other than the fact, so I guess I should say in the original differential equation, y can't be negative. But if you look in our equation, because it's squared, there's no way that y could be negative. So I guess we at least wanted to think about that y couldn't be negative, but there's no possible value of x in our equation that could make y negative. In 2, divide the y over, multiply the dx, take your antiderivative, you got your natural log absolute value of y equals the sine x plus c. Fill in your point to get that c is negative 1. Fill the negative 1 back in, and then it's your choice if you want to resolve the absolute value right now. That's what I'm pointing to with the black. Remember, you resolve all plus minuses and absolute values with your initial point. Because y was positive, we could say it's just y. Or if you wanted to switch to exponential first, then it would be absolute value of y equals the e to the sine x minus 1, and then that absolute value would be resolved by that the y is positive. So it's your choice, and you'll see on a lot of the problems, I'll show both of those options of where you want to resolve the absolute value. And it's really just your preference at which spot you want to resolve it. We need to think about in our actual equation, no issues with things being undefined. In the original, there's no issues with things being undefined. In 3, multiply your dt over, divide your y over. It's probably easiest to leave the 5 over with the dt rather than bringing it with the y. Do your antiderivative, fill in your point. We get c is natural log of 100. Resolve your absolute value. We had that y was a positive value, so it just ends up as y. Do your exponential. Now, you could leave it as e to the 5t plus natural log of 100 in a free response question. That would be full credit. This one's free response, so you could leave it like that and you get full credit. But if it's a multiple choice, they're probably going to have it look like the boxed answer I have there. So you need to at least be comfortable. Adding in the exponent is multiplying separate terms with that base, and then e to the natural log of 100 is just 100, so you can swing that out front. Okay, so need to at least be comfortable to recognize that in a multiple choice. In our final equation, so if we look at the actual equation, no issues. If we look at the differential equation, no issues with undefined. So we're in good shape. No need to restrict our domain. In 4, add the e to the x over, multiply the dx. We'll take our antiderivative of both, sub in your values to find your c. Multiply the 2 over, take the square root. Now in front of that square root would be plus minus. So we have to think about, well, what's our y value? Y is supposed to be positive, so in front of the square root we should have a positive to guarantee that y is positive. The point will determine your plus minuses and your absolute values, how you should resolve them. So we need to at least think about, are there any issues with undefined? Well, e to the x is always positive, so that radical will never be negative underneath. There's no denominators in our differential equation, so no need to restrict our domains at all. Number 5, we can subtract the y times y times x plus 1 over to the other side. You can divide by y. Now, you can choose where you want to put that negative. I chose to put it over on the left so I wouldn't have to distribute it, but it's really just your preference. Sub your point in, find your c, which you just get as 0. You can resolve your absolute value right then by making it a y, or you can wait till you get the y by itself. But in either event, you get that exponential. No issues with the exponential for undefines, and in the original, no issues with undefines. In 6, divide the y over, multiply the dx over, take the antiderivative, we've got our absolute value. Sub in your points, you get c as a half. Now notice with this one, when we're resolving our absolute value, it would have to end up as a negative y. So if you like to switch it to exponential first, notice um, in the part on the left, we have absolute value of y equals the exponential. Well, then that absolute value of y should end up as negative y. So when you divide the negative over, you get negative and then e to the whole exponent. Or if you like to resolve the absolute value right away, you'll see in the part on the right, that becomes natural log of negative y and then work to get the y by itself. No issues with undefines in our equation. No issues with undefines in our differential equation. So no need to restrict the domain. In 7, divide the y squared plus 1 over. The antiderivative of that would be arctan. Put in your values to find your c. Once you get y by itself, y would equal tan of x squared plus pi over 4. No issues with undefined in the differential equation, but we do in our regular equation. Tan is undefined anytime it is at pi over 2, 3 pi over 2, and so on. So any of the odd pi over 2s. So if we look at our initial point, our point was 0, 1. So we need to be thinking about in between pi over 2 and negative pi over 2, because that's where x equals 0 would fall in a continuous section. So we want to take the x squared plus pi over 4 and set it equal to both negative pi over 2 and pi over 2. Well, it'll never equal negative pi over 2, because if you subtract the pi over 4 over, you get negative 3 pi over 4, and a square can't equal a negative. But in the other one, if you subtract it over and take the square root, you get x is plus or minus square root of pi over 2. So x would have to stay in between those, because we need a spot where x equals 0 would fall. Notice there's no equal to's because it has to be an open interval. Divide the y over. I pulled it out as a 2/3 in front of the 1 over x just to make it easier to think about. Take your antiderivative, fill in your point, get your c, resolve your absolute value with your point, so it ended up as a y. Since there's natural log on both sides, it's just the insides are equal to each other. So some things we need to think about. In our differential equation, x cannot equal 0. So based on that, we need to be on one of the sides of 0. Because our x value that we used was 8, we need to be on the right side of 0. So we would want x is greater than 0 for our restricted domain. All right, we're going to be day 2 in the notes packet. We have that the rate of change of a certain function is proportional to y. So what does this mean? Well, that means proportional. So if we divide, we should always get the same value back. So our derivative divided by the original function always gives us the same value. Or in other words, if you multiplied the y over, it's saying our derivative should always be the same constant times the original function. We'll take a second and think about what type of function is this? Are there any functions that we've seen so far this year that when you take its derivative, it's just a constant times that original function? And we'll find out what that's going to be in a second. So if we go down, we're going to solve this differential equation. So we're going to divide the y over, multiply the dx over. So we're going to have 1 over y dy equals k dx. We're going to take the integral of both sides. Oops. This will give us natural log absolute value of y is equal to kx plus c. We'll do our exponential form, so we'll have absolute value of y is equal e to the kx plus c. We can write the right-hand side as e to the kx times e to the c. And e to any constant will just be some other constant. So we're going to rewrite this as absolute value of y, and I'm just going to make it a c out front and e to the kx. Well, based on the absolute value, that'll either be a positive y or a negative y, depending what point we're working with. Well, no matter which one it is, if it's positive y, then it would just equal ce to the kx. If it's negative y, we'd have c equal to the kx, we'd have to divide a negative 1 over, which would still be some constant. So really, we could write it like this, where the c is just some either positive or negative constant. And the sign of it would be dependent on our point in the absolute value. So notice the type of function we were working with is an exponential function. Something else to note is notice the point 0 comma c would be on this function. So c actually ends up being our initial value of the exponential function. So just to bring it back to exponential functions, we knew from before our derivative of 2 to the x is 2 to the x natural log of 2. Well, this is our y, and this is our k. Because if we divided the 2 to the x over, that's saying our derivative, dy over dx, divided by our original function, is always the same constant. It will always be natural log of 2. So when you see that phrase, the rate of change is proportional to the original function y, it needs to pop in your head that we are working with an exponential function. You don't want to have to solve the differential equation each time. We want to be able to jump right to the fact that it is exponential. So if we go down to the bottom, we've got in 2001, the population of Kushtown was 25,000. 2006, it was 29,400. And then we've got that key phrase there in green. The rate of change is proportional, and the change is proportional to the population itself. So that means our differential equation solution must look like that. And we just saw that that means our actual function should be exponential. Now we just have t here instead of x, but same idea. So c times e to the kt. 2 points that we know. We know initially in 2001, because we're doing years since 2001, we have 0 comma 25,000. And then 2006 is 5 years later. We have 29,400. Well, our c value is just that initial value. So we've got y equals 25,000 e to the kt. To find the k, we can just sub in our other point. So we'll sub in the 29,400 is equal to 25,000 e to the k times 5. We can divide the 25,000 over, or sorry, yeah, 25,000 over. Now that can reduce some. We can divide by 100. And if we kept dividing, that would give us 147. over 125. And 147 could be 49 and 3. So we have 7s and 3s will go into the top, 7 and 3 won't go into the bottom, only 5 goes in. So that looks like it's as low as it'll go. And we've got e to the 5k. We'll switch to log form. That would be natural log of 147 over 125 is equal to 5k. Or in other words, k is going to equal 1/5 natural log of 147 over 125. Now, let's say this is a no calculator thing on a test. You don't have to reduce that fraction. You could have just left it as 29,400 over 25,000. That would be perfectly fine. So our final equation then is we've got the 25,000 e, and then we have k times t. Well, we just found k was 1/5 natural log 147 over 125, and then t. Now, you won't have to restrict your domain for this because we got an exponential here. Those are all good. And it was just constant times y in the original, or in the differential equation. All right, so I'm going to copy that equation over just so we have it, because we will need to know it in this problem. And I forgot my t. So we want to know what is the actual growth rate as a percent. Well, let me go off to the side and just put a simple exponential function. If we had this, it would be easy to tell that our growth rate would be 3%. So your growth rate is always 1 plus some rate, and that r is your growth rate. Well, and we can find that if it's just raised to the t. Well, we could write this as e to the 1/5 natural log of 147 over 125, and think of that as all being raised to the t. So really, we want the inside of that parentheses to equal 1 plus r. So on the right side, that's really some decimal that's 1 point something. So if we punch the right side in the calculator, we'll end up getting 1.0329551 and some other stuff. Subtract the 1 over, so that means r is just 0.0329551 and some other stuff. So if we rounded our percent with AP rounding, this would be 3.296%. So the main reason for that is that it just gives us a little bit better sense of how fast is this exponential function growing. If you've got it as e to the 1/5 natural log of 1/47 over 125 times t, who knows how that's growing? Is that a big growth? Is that a small growth? You'd have to think about it to figure it out. But just by finding this r value, we can get a little bit better sense. Okay, it's growing a little bit more than 3%. All right, and then we want to use our equation that we have there to predict in 2010. Well, remember, we were doing the years since 2001, so 2010 would just be 9. So we'll have 25,000. We'll have e to the 1/5 natural log 147 over 125 times 9. And really, we could use that equation to predict any population value right now. So 33471.34 we would get. So we've got people, so to the nearest people, it'd have to be a person, it would have to be a whole. And on the AP, if it's not going to be a 3 decimal places type of thing, they'll usually tell you specifically round to the nearest person or whatever. One last example for this video. Buying power of the US dollar in the year 2000 dropped to 73 cents in 2005. So from that, we're going to get 2 points. So we're going to let t equals 0 be 2000. So that means in year 0, we're thinking of the dollar has a buying power of 1. That's like our initial thing. And then in 2005, so 5 years later, it dropped to 0.73. What will the buying power be in 2010? So we want to know 10 comma something if the rate of change is proportional to the value of the dollar. All right, that last line, we need it to go off in our head. Oh, we're dealing with exponential. We've got y equals c times e to the kt. Let's just fill in what we know. Our initial amount was 1. We can sub in our other point, the 5 and the 0.73. So we'll have 0.73 equals 1 e to the k times 5. Divide the 1 over and take the natural log, so we'll have natural log of 0.73 equals 5k. And divide the 5 over, we'll have k equals 1/5 natural log of 0.73. So the k is often going to be messy. So don't be afraid if you do get something messy. So our equation now is y equals 1 e to that 1/5 natural log of 0.73 times t. And we want to know in the year 2010, so 10 years later. So we can just fill in 10 for t. And we're dealing with money, so we have to round to the nearest cent. We get 0.5329 when we sub that in. Or in other words, we get $0.53, so 53 cents. So the key thing is when you see that phrase that the rate of change is proportional to the original value of the function, you need to make the connection, okay, that's exponential. I should work with c times e to the kt. Okay, you don't want to have to every single time solve the differential equation. That'll just take extra time. Have a great rest of your day, and we'll see you tomorrow.